everyone. I don't think any more of us will be joining us. My presentation will be about Capsicum and Casper and how the Capsicum and Casper help us to solve the security problems, and about how which problems Casper and Capsicum create and how we try to manage them. So first of all, thanks Brooks for borrowing me adapter, because I had a little bit problem with my laptop before the presentation, so thank you very much. So my name is Mariusz Zaborski. I'm working at Will Systems. We are a security vendor. We're building appliance for monitor and recording network traffic. I'm also a FreeBSD developer. I'm a FreeBSD developer almost 1 year. So it will be, I think, in a few weeks my anniversary. So one of our presentation looks like that. We will discuss, do we need Sandbox at all, or maybe we don't need, and the rest of my presentation will have sense and we can go to home. Or if it has sense, then we will discuss 3 different sandbox techniques, starting from seccomp, then we will discuss output and pledge, and finally the Capsicum. At the end, we will be discussing the Casper. I will show you 2 architectures of Casper, and we will be discussing the advantage and disadvantage of both of them. So let's start. Do we need a sandbox? So let's think that for a moment. Do we have in our operating system a program which can access all our data, which can read our data? Yeah, we have a lot of them. For example, even such simple like that. If somebody would find a bug in a program like that, he would gain access to our data, even the private one. He could even create a connection to the server and send them over the network with it. But if this program could have only 2 descriptors, one from which he could read and another one which could he only write, then such security of such program would rapidly rise. So every time when we're speaking about a system in which we don't have control what program is going on, to which data it have access, we speaking about ambient operating system. So do we trying to solve somehow ambient authority? We trying not only solve ambient authority, we also trying to solve the method of exploiting the bugs, right? For example, we have ISLR or canaries, which are prepared for solving or preventing from exploiting one of another vulnerability. So they are not always successful. They sometimes only make the exploiting harder. For example, NXBit is it's preventing it's telling processor to prevent some area of memory from execution. But researchers came up with idea to use return-oriented programming to look for such called gadgets from which we are building the exploit. Gadgets are mostly in the part of memory which don't have this flag. So of course, if those techniques would work, or they would prevent most of our bugs, or make the exploiting so hard that it wasn't, the cost of the finding the bug would rise rapidly. Of course, finding one simple bug wouldn't matter, right? Because we have few of them. And this isn't the truth. We have a lot of bugs in our operating systems. Two of my colleagues, Gilbert Colvin and Mariusz Zaborski, did some testing in around 2010-2014. And they came up with a lot of bugs from FLPG, for example, around 1,000 bugs. And all of this, most of the bugs were security bugs. And the same story was with Flash or with Adobe Reader. And we have a lot of bugs in our software, and even if we would think a little bit about how the bugs was repaired, we could find that 1,000 bugs isn't one line of code, right? There are a lot of lines of code which should be changed to cover all those bugs. So of course we should ask how many bugs were introduced after that, right? Because new fixes create new bugs. So maybe instead of trying to solve exploit techniques or preventing from exploiting, we could separate the process from the system. For example, using seccomp. Seccomp is a little bit old technique. It was presented in 2005. I said a little bit old because all of techniques which I will present will be much younger. It was presented in Linux. Seccomp gives us a simple system called seccomp, which can work in two modes. First one is called strict mode, which allows us for very simple things like read, write, or close. And with this strict mode, we cannot do a lot. It's a very unflexible method. We could only do very simple things. But for example, in our cat example, it would work quite well. Another mode in which seccomp can work is a filter mode. It's based on Berkeley package filter, and it's filtered which syscalls can be used and which parameters to the syscall can be passed. So here we have a simple usage of seccomp. It's not pretty nice, right? It's just some declaration. In my opinion, it's pretty awful. We new programmers don't know what it's about. This code is from the OpenSSH program. So the maintaining of such code isn't easy, and every time when we update or change something in our code, we need also to change our filters. So programmers from seccomp propose also the alternative method of creating those filters by presenting libseccomp, which makes it a little bit easier, but still we need to put a lot of effort to making seccomp very efficient. So another method which I would like to present is Fletch. Fletch is very new method. It was, if I remember correctly, it was presented last year. It's coming from OpenBSD. In my opinion, it's very similar to seccomp, but the difference is that we don't need to define the filters. Programmers did that for us, which our life is a little bit easier. The concept of seccomp is that we can divide any program to two parts. One is called initialization phase, where we can define all the flags or the rights which our program needs. And the second part is the main loop, where we do a very complicated algorithm which could be potentially active. And Fletch already changed its name from Pain. To be honest, I don't know why. Pain was a pretty nice name, if somebody would ask me. And Pledge is very easy to use. We have just two, we have simple syscall, which allow us to pass the premises that we want to have. And in theory, the white path with program can open. This is the list of paths that the program can open from file system. As far as I know, and I was checking the code last night, this white path is still not implemented. But what people could think about Pledge is very easy to use because it's used in over 400 programs. So we have a lot of promises. There are 24 of those promises. One of them is SDIO, which allows, it's mostly used, I think it's used by all the programs because it's all us for very simple and basic performance like malloc. Other promises is airpath, which allow us to access all the file system, but we own. And the opposite or other promises is wpath, which allow us to enter all file system, but also we can do some writing, which is very interesting, and I would like to point it out that we have also two promises, pros and exec, which allow us to form and execute another program. So here we have a usage of Pledge in a simple program called cat. We just analyze the code. We know that cat don't do anything fancy. It just opens some file, it just writes to std_out or to different file. So we need only two promises, SDIO and airpath. But unfortunately, I think Pledge have few issues which should be solved. One of them is that if we are using exec promises, the new program which is started after calling exec is not sandboxed anymore. So if we have these promises and we can open any file, we can just simply escape from the sandbox, which in my opinion is a little bit mistake, or even not a little. And every fork program is using it, so in my opinion, every fork program isn't secure enough. Another thing is that programmers from FreeBSD decided to hardcode the paths from the user one in kernel. In my opinion, it's not very clean, and I would look for other methods to do that. And which also is very interesting, in my opinion, is very interesting that not every program we can divide into only two parts, which is initialization phase and main loop. What if we want to reload the configuration? What if we want to change something? What if the promises would change something? We need to call exec and just fork the new process and be potentially exposed from some risk. So at least Capsicum. Capsicum is a FreeBSD sandbox. It was presented in 2010 by researchers from Cambridge and from Google. We can divide Capsicum into two parts. Which one? One of them is a very tight sandbox, in which if we enter the bit, we don't have access to any global namespaces. So we cannot open files, we cannot ask for keys, we cannot work with jails and so on and so on. So, but we still can use the capabilities which we have. So, for example, if we would open the file before entering the sandbox, we still can use this descriptor. So this this is quite similar to Pledge, when we just have some initialization phase, which we can initialize our program and then do the hard algorithm. but which also is very interesting in Capsicum, we can limit descriptors even more. So if we have a descriptor for, so we have over 80 capabilities in Capsicum, and we can say that this descriptor is read-only, this descriptor is write-only, and kernel will forbidden us to mess them up. And what is very interesting, and which, for example, we are using in our product, is the capability which allows us to append only. So, for example, if we have a process which logs all the data which came from network or also something else, we are dumping the packages to the file which is append only. So if somebody would break to our process and would try to exploit it, we will record it, and we will not allow him to remove that record from our log. So, like I said before, in Capsicum we have two ways to obtain the capabilities. One is in the initialization phase, so before entering the sandbox, and another way is by delegation. So one process can delegate me some right that he has. This is done by the file descriptors. And thanks to the Unix domain sockets, we can pass over the descriptors from one process to another one. So, unfortunately, Capsicum isn't so easy to use like Pledge, for example. But it's what is giving us a little bit more flexibility. So here we have an example how the Capsicum is used in Unix program from FreeBSD. First we install it, we also need to analyze the code. So after the analyze, we came up that Unix only needs two descriptors. One from which he is reading, and another one from which he is writing, to which he is writing. So we declare the two capability, we open the descriptor, and we limit them to be only read and write, and also we would like to do the f-stack on them. And that's all. And after that, we can enter to the sandbox. And our process is very secure. There's no way to obtain more writes. We cannot do anything else than to write or read from those both descriptors. And even if we would find a bug in Unix, we would just can somehow interact. We can only write additional data to the file, but if this file from which we was reading was already malicious, it don't have any matters. So if we are telling about Capsicum, we also, I mentioned also about delegations. So delegations are a little bit more complex template in which we have two processes. One which have access to some resources, for example, to file system, or he can resolve some names for us, or he has access to database. And we have also the sandbox process, which is doing the hard, very complex algorithm. So the privileged process can, for example, give some descriptor to the sandbox process to say, hey, this is the process, please do something, this is the descriptor, please do something with that. For example, I compress it. And if the file which was read was somehow malicious, it just would be exploited in the sandbox process. So we are still very safely. And the privileged process, even if you don't know if the sandbox process was compromised, it will only give another descriptor. So it would only have the rights which he already had, right? Because he still can only read this one file. So implementing of this template is very creates a lot of duplicate code because we often need to fork from the original process. We need to implement communication between those processes. So then the idea of Casper was created. So Casper allows us to provide us functionality which are not available, in capability mode by a very simple API, which is very similar to the original one. So first approach which was implemented was Casper as a daemon. We had a Casper which started with the operating system. We had some services which was executed. Services in Casper are just the, some part of some modules which will be replied often in the sandbox, right? So, for example, we have a DNS service which provides us a very easy access to the DNS server. And if you would like to implement, for example, a DNS server in TCP dump or anything, it will be very similar approach. So why duplicate code? We can use the Casper daemon. So we also had a list of the services as a Casper. The idea was that we can install, for example, additional services from the ports. We also had two libraries. One was the lib Capsicum, which provides us inter-process communication for Casper and for the service Casper and for the process, which was Sandbox. And lib Casper, which allow us to create new services. So this is how the Casper daemon was work. It was starting with the operating system. So the init script, which would start the Casper daemon. And as we can see now, even now, it has some problems because init is started by root and in the root directory. So Casper D automatically would gain privileges of root, and also it has a current working directory set to the root. So after that, Casper was forked for one time. The new process was called Zygot. It was a very lightweight process, which in idea should be very easy to fork, very quickly to fork. It didn't have any additional memory, usage of memory. He didn't have any additional descriptors and so on and so on. Casper also created then a Unix domain socket, which allow other processes to communicate with him. So after that, some process could ask Casper for service. So he would connect. He would connect by Unix domain socket to the Casper. After that, Casper would be forked from the one zygot, creating two zygots. And one of the zygots would be transformed to the service. After that, the service will be passed to the process, and then the communication between process and service wouldn't be anymore considered by Casper D. Casper D can now wait for another process that needs some services, and process can be now sandboxed. Unfortunately, this approach had a lot of issues. For example, like I mentioned, the process which was asking Casper for new service had different credentials than the service. So this was really easy solved because Unix domain sockets allow us to obtain the credentials in a secure way, obtain the credentials of another process. So we could just set with and set heap and set groups the right credential of the process. But some of these problems wasn't solved very easy. For example, we have a different resources limit. or we had a different MAC levels, or we had different working directory. But that's not all. We also had the different CPU sets. So we could say that we want that this process would only run on this CPU, but the service would work on the different one. So we would gain a more rights. What is also very interesting that we had a problem with the so-called subprocess in the shell. This method allows us to pass the output of 2 or more comments from, or 1 comment, from output to, of this comment to another process. And this was done by file descriptors. So when we are opening, doing the open syscall on such, in such process, we would open the descriptor that was open before that. So service, Casper service, didn't have that descriptor, so it couldn't be done. So we had also a very interesting problem with Sandbox and ping, which turns out that we can change the routing table of one particular command in our operating system. And of course, service wouldn't inherit those routing tables. So ping would ask for example, Casper to resolve some names, but the routing table which we was asking wasn't be used. So we also the Casper daemon was harder to audit or key trace. And we also had a one point of failure. So if somehow Casper would fail or would be some bug in Casper and the process would exit, we no more have any process which provides us new services. So we just, it's turned out that our system is no longer Sandbox, because most of the programs that are Sandboxed with Casper and Capsicum cannot work only with Capsicum. So the new architecture of Casper was presented. We decided to fork from the original process, which solved most of our problems. We don't need to think about credentials. We have the same routing table. We have the same working directories, and more and more and more. And also using pfork allow us to do it in very elegant way, because the new process don't so if we would PD wait, for example, for any process, the process which was PD forked won't be the status from this process won't be collected by PD wait. PD wait. So we also reduced the modules which we needed. We now only have lib Casper and service. So if we would see the previous implementation, we always need the lib Capsicum, and we also need the which was inter-process communication between Casper and process, and we also needed implementation of this service. But now I don't think we need to separate those two things. We're also doing the dynamic linking with the Casper, so we only register the services that we need. Maybe it's not clear enough. So libcasper is a library which provides us the API for communicating with the new process and to create it. And it also registers the services that we want to use thanks to the constructor in the library. And the API of the solution wasn't changed at all. But unfortunately, we still have some problems with Casper. For example, if we create the Casper and we start to change some capabilities, or we change the directory of our process, it won't be inherited by the Casper service because we don't have such API. And another problem is that we cannot anymore disable Casper globally in the system. So previously, if some process started to use Casper, some program started to use Casper, and it still didn't work, the administrator could choose to disable Casper globally in the system and still work with this program without the sandbox. Now we need to rebuild the program. So as I mentioned, we have a few of the services. Right now we have them 5. For example, we have the DNS server, which provides us this service allows us to resolve names, DNS names. And the other, for example, is the random, which provides us a simple API to obtain some random numbers. So here is how we could use Casper in our program. So first we would need to fork or create a Casper connection by calling cap-init. Then we create the systems that are interesting for us, for example, system DNS. And then we even can limit the Casper to allow us only to resolve names and only on only in IPv4 or IPv6. In this case, we want both of them. And after that, we need also to change the original function from the libc to the new Casper function, which is very similar to the original one, but it has additional attributes called which provides the connection with the Casper. So my future goals of this of Casper is in Casper and Capsicum is to lower the bar which is needed to use the Capsicum and Casper in the process. And I also would like to implement the file system, which provides a service to obtain some files from the system to open files, and like we see before, there is also needed still to check if the Casper is this Casper is needed in this part of code. So we have if we define which function do we need to use, and I also would like to remove that. So thank you very much. I hope that wasn't very chaotic, and you get from my presentation some main points. And do you have any questions? Okay, so thank you very much.